Thanks, John, for introducing. Good afternoon, everyone. Thanks for being here. Today, I'm excited to share how we transformed aggregations in Opensearch to achieve up to 100 times performance improvement. Just a quick intro. My name is Ankit Jain. I am an active maintainer of Opensearch and contributor to Lucene. I work as a software engineer on the AWS Opensearch service team, and where I lead the efforts for performance and large-scale search infrastructure. I've spent over a decade with massive Opensearch deployments, solving tricky performance issues and debugging challenges. Feel free to reach out on GitHub or Slack if you want to chat more around that. Here is a quick look at the latency improvements we have seen over the versions of Opensearch for date histogram aggregation queries from the Big 5 benchmark workload. As you can see, the gains are massive, in some cases up to 500x faster. By the end of this talk, we will understand what drove these improvements and why that gray bar, for example, which represents minutely aggregation, looks a bit different than the others. When we started this performance improvement journey, we did not expect such dramatic results. At every point, we were just focused on doing our best, diving deep, asking the right questions, and trying to understand the system better. And in the process, we ended up achieving something that we did not really imagine. This is going to be the structure for our talk today. So we will spend some time going through the basics, like query DSL structure, what bucket aggregation means, how the aggregation executes in the Opensearch engine, and some of the optimization strategies that we employed to get these performance improvements. And towards the end, we will talk about some of the things that we are planning to do next, and hopefully have some time for Q&A as well. Let's start with a quick look at a basic Opensearch query. This one uses the sample flights data, right? And filters for flights where the destination country is US, and also groups by the destination airport ID. When we think about this query DSL in the context of Opensearch dashboards, the size is what represents the number of documents that you will see on the Discover page. The aggregation is something which represents how we are able to build the visualizations. And filter is something which applies to both aggregation and the document retrieval. So that is something common which applies to both the fields. This screenshot shows how the query DSL response looks on the dashboards page. So we have the flight information aggregated by hour of the day, and below that, we have the list of raw documents. And this screenshot shows how the response looks when we add the filter for destination country as US. And you can see that the overall number of hits has reduced from 300 something to 44. And similarly, the list of raw documents has also decreased quite a bit. Let's quickly talk about the different aggregation types that we have in Opensearch. At a high level, we mainly have 3 types of aggregation. Metric. This is something which can be used to compute min, max, sum, or average. We have like bucket aggregation. So this is something which can be used to group documents together and count, like date histogram, terms, or ranges. And we have the pipeline aggregation, which can be used to combine multiple aggregations together, where the output of one aggregation is used as input to the other aggregation. Very similar to the pipe operator that we have in shell. So for today, we are mainly going to focus on bucket aggregation because that is where we have seen some of the biggest improvement. Let's look at a few sample query requests and responses for bucket aggregation. Here is an example of a date histogram aggregation that aggregates the logs information on the basis of month, right? And it just simply returns the number of documents for each month. This is something which can be used to understand the time series data much better. This one shows a range aggregation. It groups the number of bytes based on the range that we provide. And this is something which can be used to understand the distribution of data better. Here is a look at the default aggregation execution flow in Opensearch. So let's say you are querying something like status code equal to 200 and operating system is equal to Android. So the way it works is, so first, all of this happens for every shard in Lucene, right? So it will try to build a doc ID set iterator for each of these queries. So if we pick, let's say first query where status is equal to 200, we can see that the matching documents are 1, 2, 5, and 700. And similarly, for operating system is equal to Android, the matching documents are 1, 4, 5, and 700. So now when we want to do AND of these together, so Lucene will combine the two doc ID set iterators and make another doc ID set iterator out of that, which will skip through matches that are not in both the queries. For example, document ID 2 and 4. And now, when we build this doc ID set iterator, it will be passed to the aggregator. And that aggregator will just simply stream the list of document IDs, and it will use the doc values data structure in Lucene for getting the value for each doc ID of the field that we are aggregating on and build aggregation using that. For example, here we are trying to build the average aggregation. So it will just read the size, value of size for each of the matching documents and compute average on top of that. Though simple, this approach is very elegant because it enables the creation of complex sub-aggregations. So think of it like a waterfall, right? As the document IDs are streamed, they flow through different, through each collector, right? Collector can be thought of as an aggregator. So they flow through each aggregator, ensuring they are correctly mapped into both top level and sub-level buckets. For example, if you want to see the HTTP status code distribution for every month, we can use something like this. So 2 years back, we started really looking deeply into how we can improve the performance of such aggregations. And one of the things that I always do when we want to understand performance is I take the query, a single query, run it in a loop on a single node deployment, right? And then I start collecting flame graph on top of that. So when you get the flame graph, so the width of different stack path, like different stack traces in this histogram gives you how much time each path is consuming in the overall latency. For example, if the query is taking 7 seconds and we have like this blue stack on the right, so we can see this is roughly like 40% or 35% of the flame graph. So that means probably 35% of the time is going in this code path. So based on this flame graph, I was able to conclude that we have these limitations. So first limitation is the latency for this aggregation operation is proportional to the volume of data. For example, if you want to compute aggregation on 1 month, then it takes 1 second. And if you want to do it for a year, it might take up to 12 seconds, right? And one of the other challenge I noticed from this flame graph is if you have like too many buckets, right? Let's say you want to do a minute aggregation for 1 month of log data, then the number of buckets is, as the number of bucket increases, the chances of running into issues related to hashing collision. For example, when you are mapping these documents into a bucket, you are using the hashing technique. And as the number of buckets increases, the chances of a hash collision increases. And resolving those collision takes time. And it might increase the latency further. With that context, let's take a look at some of the optimization strategies that we employed for achieving those performance gains. So one of the first things that I tried to do was I took a query, a big query, which does a monthly aggregation on 1 year of data, right? And I thought, okay, it is just returning, count for each month. So essentially, the response can be thought of as just 12 numbers. And what if I run it as a multi-search query, right, where each query is doing a 6-month aggregation instead of 12? And with that, one of the things I noticed, the query time decreased from 7 seconds to about 4 seconds. But so when I went with this to the community, some of the feedback I got from there was, this is essentially a zero-sum game because we are trying to execute these requests concurrently. So we have not really decreased the number of CPU cycles required for each operation. It's just we are doing it concurrently. And if the CPU is saturated, that concurrency is not going to give us any gains. With that knowledge, I tried something else called data slicing. So what I did was, I said, OK, let's forget about a year. I want to just get the number of documents for this 1 month. And how can I do it in a quick manner? So what I did was, I rewrote the whole thing as this query, right, where we are saying, give me the number of documents from December 1st to December 31st, right? When I say size 0, essentially I don't want any raw documents. I just want the number of documents. And that's why I said track total hits to true. So now you can see here that the took time dramatically reduced. So here you can see the took time is about 162 milliseconds. And if we were to even repeat this operation for 12 months, this will be close to 2 seconds, and which is already a very significant improvement over 7 seconds. So at this point, I was like, oh, yeah, this is something which can work very well. So what we decided is, OK, we can rewrite the yearly aggregation as filter aggregation. So what we want to do is, we essentially want to compute the number of documents for each month filter. So before we understand why this improves significantly, we want to learn a bit more about the points index. So Lucene uses points index quite extensively for querying the data. but for aggregation, it is hardly used at all. So for that, we mostly end up using doc values. So here we want to, and so this point index is something which is stored as a BKD tree in Lucene, right? And if we want to understand BKD tree, we want to understand some basic data structures which will help us understand what a BKD is. So I think everyone knows about BST, which is like nothing but a basic binary search tree, where we have like two children per node, and it is like left subtree contains the smaller values, right subtree contains the larger values. And from that, it's very easy to derive something called B tree. So B tree is just the more dense form of a BST, right? Instead of having like instead of having just two children per node, we can have, up to like 10, 15, 20 children per internal node. And also another thing that B tree does is all the data is stored in the leaf nodes. We don't have actual data in the internal nodes. From that, we can talk a bit about KDB tree, right? So KDB tree is a k-dimensional B tree. So let's say if you want to store geo points, or you want to store points in a 3D space, x, y, z coordinates, right? So one way to do that will be a k-dimensional B tree. So what you can do is, for example, on level 1, you partition on the basis of latitude. Now on level 2, you can partition the space on the basis of longitude. And then at level 3, again on latitude. So like in a KD tree, every level is partitioned on a different dimension. So that way you can gradually keep partitioning the space until you are able to find the values that you're looking for. And BKD tree is nothing but a more disk efficient implementation of KDB tree. So we don't necessarily need to go into details of BKD tree for the purpose of this talk, but it is just it just ensures whenever you are trying to look for a certain value, the number of disk seek operations that you need to do is minimal. So I think even though we talked about KDB tree and BKD tree a bit in the previous slide, but for this specific talk, we don't need to worry about that. So here we have a simple one-dimensional tree, right? So this is like we can think of it as a B tree, which has only 2 children per node for simplicity purposes. And none of the data is stored in the internal node. The internal node just has the range of documents below that node, below that, like in that subtree, and the number of documents. And in the leaf node, we have like say documents from 1 to 100, 101 to 200, and so on. So now let's say you want to, on this tree, you want to know how many documents are matching from 351 to 771. So here 351 is which is inclusive, and 771 is excluded. So a good way for doing that is, so you start top of the tree, you say, okay, I'm looking for documents for this range, and from top it says, okay, this is something which intersects with what I have, right? So you go deeper into the tree towards left and right subtrees, and until you keep having match, you keep going down in the tree. So one of the optimization that we can do over here is, for example, if you go to the node from range 1 to 200, right? or towards the leftmost, you can clearly see without going to its children that the number of matching documents is going to be 0 because we are looking for 351 to 771. So 1 to 200 is not going to have any matches. Similarly, if you look at the node with 401 to 600, we know that everything within this subtree is going to be a match. So we don't even need to go to the leaf nodes. We can return from here itself saying, OK, I have like 200 matching documents. Coincidentally, in this example, we have like, one-to-one mapping that this like 401 to 600 has 200 documents, which might not be the case practically. Like even though the range might be 401 to 600, the number of documents within that tree could only be 150. And so, as you can see, right, we can very easily recursively return the response to the top and get the final response, which is 420, right, without going through each leaf node in the tree. As you can see, we are able to skip like bunch of leaf nodes, right? And the only ones that we had to go through were the ones storing partial data, like the leaf nodes that were partially intersecting with this range. So after this optimization, we were able to see a massive improvement because we are just counting the number of leaves. We are not actually visiting each value as we were doing in the doc values model. So essentially, earlier it was like a linear operation, ON, but now we are just doing a log n operation because we are just going in the tree, skipping through like most of the leaf nodes and just getting the response from the ones that we care about. But this approach still had some limitations. For example, if the number of buckets is a lot, then we are like doing log n for each bucket. So in practice, for example, if you recall from the example we had earlier, we want to get the log data, monthly log data for the whole year, right? So essentially, we have 12 buckets. So similarly, in production, we can have customers doing minutely or hourly aggregation for years worth of data, which can have like 10,000, 20,000 buckets. So in those cases, this model does not scale that well because you are like starting right from the top. You need to go, because in practice, this tree can be really deep, right? Even though here we have just 3-4 levels, in production it can be like 10-15 levels deep. So for each bucket, you start top of the tree, you collect the documents you are interested in, and then return the response. So that latency for each bucket starts adding up. So at least we want to just revisit the benchmark. So now we are able to explain how we were able to have this performance improvement from 2.11 to 2.12 for daily and hourly aggregations, because daily and hourly aggregations did not have significant number of buckets. So just with this approach, even though we were doing the traversal per bucket, we were able to see a significant improvement up to 50x. So while it was good, but we felt that the gray one, which is a minutely aggregation, that is something we still can do much better about, right? And that is when we came up with this completely novel approach called multi-range traversal. So what we did was, let's say we want to collect the documents for these 4 buckets, right? So we have put these buckets at the bottom, and so for example, the range is -100 to 151, 201 to 301, and so on. And now what we wanted to do was, instead of doing individual traversal for each bucket, we wanted to do a single, slightly more expensive traversal, but a single one, and collect documents for each bucket in that single traversal. So what we did was, so we started with kind of a two-pointer approach, right? Where we started top of the tree, and we had the second pointer to the first bucket, right? As long as the values that we are seeing in the tree are less than the maximum of the first bucket, we can keep collecting the documents in the first bucket. The moment we encounter a value which is bigger than the maximum of the first bucket, we want to move to the next bucket because we are doing the traversal of the tree in order, and we cannot get any more relevant documents in the first bucket. So as you can see here, right, after we collect first bucket, we, without going completely back in the tree, we automatically move to the second bucket, right? And this ends up saving a lot of operations, especially when the number of buckets is very high, right? So you don't need to go into the tree from top down again and again. So this is how the final collection for this specific case looks like. So we are able to collect the documents for each of the bucket while still being able to skip some of these leaf nodes. For example, 301 to 400 we could completely skip as it is not overlapping with any of the range we are interested in. And 401 to 500 or 501 to 600 is something which was completely subsumed in one of the range we were interested in. So that is something we could again completely skip altogether. So after doing this approach, we were able to, in the earlier benchmark that we talked about, right? So we were not able to improve the minutely aggregation. But in 214, when we went ahead with this, we were able to improve the minutely aggregation as well. And I just want to quickly zoom in to the benchmark earlier. Because of the 100x improvement compared to 2.7 and 11, we are not able to see that after multi-range traversal, we were able to bring down the latency further from 12 millisecond to about 6 millisecond. So this is like further 2x improvement, and combined with the 50x that we had earlier, this gives us 100x improvement in the latency. This is something, so this improvement was so impactful. We recently contributed it into Lucene as well, and now other search systems based on top of Lucene, like Elasticsearch, Solar, can also benefit from it. And soon, we should be able to see these optimizations in those engines as well. With this, I would like to welcome my colleague Sandesh Kumar to talk more about how we employed similar techniques to improve the performance for terms aggregation in Opensearch.
Hey, good afternoon, everyone. Thank you for joining. Thanks, Ankit, for setting up the stage. OK, so before I continue discussion on terms aggregation, let me quickly give a brief introduction about me. So I'm Sandesh. I work in AWS Opensearch. I mostly focus on search performance and cluster resilience. I also host search trash meetings where we discuss search-related issues. We prioritize what features we can pick up next. And so it's also an open-ended, we keep it open-ended where people bring in their half-baked ideas. And yeah, So, okay, so before we move on to understand what improvements and what optimizations we did, I'm quickly showing the performance improvements in keyword terms. So these are benchmarks from Big Five. You can see from 2.12, we did improve over 100x. I mean, the keyword terms initially used to take more than 3 seconds to run, and now they are running almost at like 20 to 30 milliseconds. Okay. Okay. Now going on to keyword terms aggregation. Here is a quick request and response structure. You can see that here we are trying to collect different buckets based on response codes. It says response.keyword because we had indexed response codes as keyword types. So, okay. Before going into what we improved in keyword aggregation, this is a quick recap on how we execute aggregations in general. So it's again like all the aggregations, it's again the same thing, where we run a query, we find the matching doc IDs, and then we go to the doc value set iterator, we collect different buckets. Again, simple approach, effective approach, but again, deals, it comes with the same set of performance challenges that as the number of buckets increases, which is usually the case with keywords aggregation, or if the data volume increases, they end up becoming very slow. So what we did to improve it. So here I want to bring a quick analogy on what Ankit discussed right now. So to improve numeric aggregations, range aggregations, date histogram aggregations, we took inspiration from how the range query actually works, right? So in the same context, for keyword aggregations, we took inspiration on how keyword or like a simple term query works. So we don't go to doc values, like in optimizing numeric range aggregations, we did not go to doc values. We went to the point trees. So similarly, for keyword terms aggregation, instead of going through all the doc values, we relied on how terms query work, which is reading directly from posting enum. So posting enums is what Opensearch maintains for keyword fields. It has term frequencies where we can actually directly read up the aggregations. It comes with its own set of limitations that since this posting enums or BKD, any data structure, it is maintained per segment for a single field. So you can only apply these performance improvements where the entire segment actually matches what you want to aggregate upon. So so basically in our aggregation workflow, we did introduce these checks where we check that the query should match all documents within the segment. There should be no deleted documents. So all the leucine data structures that we maintain, whether it's point tree, posting enums, they don't take into account deleted documents. So basically, once you have, when you run a query, the resultant bit set is actually, it takes care of the deleted documents. But the trees, the point trees, posting enums, they do not take care. So these are some limitations that we have when running these optimization. So just walking through quickly with the optimization. So we have this posting enums, which I talked about. It maintains term frequencies. So again, keyword fields are, they are mapped to some form of ordinals. Ordinals are basically just numbers between 0 to n, where n is different keywords within that segment. So we map it to ordinals so that we can traverse it faster instead of like looking for like terms like apple, banana, or anything. It's easier to just look for 0, 1, 2. So yeah, these numbers are then converted into global ordinals because different segments can map ordinals differently because not all segments may have all the keywords. So yeah, so that's this is one of like the very simple optimizations we did. So now coming to limitations on these optimizations. So the main fundamental of these optimizations that we discussed in numeric and terms is that we are trying to collect some form of metadata from a single index structure, whether it will be a point tree or posting enums. So the limitation is it has data only about a single field. So what happens is if you have aggregations in a nested structure, you can't use them because one index structure will not have information about the other fields. And the same limitation becomes for multi-filter aggregations. Let's say you are doing an aggregation on a field A, and let's say you have a top-level query running on a different field, let's say B. So one index structure does not have information about the other index structure. So that's why multi-filter aggregations also becomes a challenge. And I think also already talked about deleted documents. These Lucene index structures, BKD, terms, enum, dictionary, they don't account for deleted documents. They are stored separately in a bit set. So that's why we also do check that whether the segments don't have any deleted documents to apply these optimizations. So looking into the limitations, I think we were able to benefit majorly because of some form of metadata which BKD or posting enums had. And the major limitation, which was not having information about the other fields, this became the major bottleneck on improving nested aggregations. So that's where we go on to what's next for aggregations. It's star tree. So this talk is not about star tree. I'm just giving a brief introduction, very brief introduction so star tree is basically a new composite index that we introduced as an experimental feature. That index, it has information about different fields, and we'll talk more about it tomorrow. So yeah. OK, so we do have a follow-up talk on star tree, where we will talk about how we improved nested aggregations and how it actually stores up the data. I think here are some of the major major Opensearch issues that we are tracking for different aggregations and some of the notable PRs. So feel free to check them out. I think that ends the talk. We are open for any questions.